All right. Another fun experiment. Okay, so go back to this guy. Anyone remember his name? J.J. Thompson. Good. I always use cartoons, so I just look funny to me. So it's just my sense of humor. Anyway, so if you still remember, J.J. Thompson used the discharge tube, break atoms apart, right? And the electron move this way, and yeah, so he discovered the negatively charged particle. Okay, now his student. So we have Francis. I don't know. It's called Aston. That's what I call him. So Francis Aston, Thomas, J.J. Thompson students used modify the discharge tube. Okay, look at what different here. So first of all, if you go back right here, so the cathode or the positive pole is on the right side. That's by J.J. Thompson. But for Aston have the negative charge on the right, which means that when the particle coming out, what is the charge of that particle? Gonna be positively charged. Okay, be positively charged particle because it's negative, positive go toward it. Okay, and he add neon, which this is similar to Thomson, use neon as well. So basically this is a neon light. That's how the same how it works. And so Aston extends the discharge tube, make it longer, and have a curve right here. And during the curve, this is the key ideas right here. He add the magnetic field. The reason for adding the magnetic field is to deflect the positively charged particle. Okay, so it will curve out like that. Hit the screen so you can see it. All right, here's what happened. So he run the electrical current. So neons kind of like a glow and then break apart. Electrons go to the left side. Doesn't do anything. Just hit right here. Hit the end of the tube. But the positively charged particle, which is nucleus, move to the right. All right, go get accelerated. Go move to the right. All right. And now here's the thing though. Here's the key. This gas is just pure neon. Just one atom, right? Just one element, not one atom, sorry, one element, like millions of atoms in there, but one element. So the nucleus, the positively charged nucleus come out, it's gonna be the nucleus of neon, just neon, right? So it's gonna be one type of nucleus. But what he found out is once this positively charged particle travels through the magnetic field, it splits into 3 particles. What's going on there? So what's going on? This is supposed like contamination. So of course he's gonna be like, is something contaminated? Of course not. This is like he gotta make sure that this is just a pure neon. Okay, nothing else in it. Right? So one neon, one type of nucleus, but it's split into 3. What's going on in there? I'm going to explain like this. All right, now look at me real quick. If you still see my video right here. So if I have a ping pong, let's say a ping pong ball, roll across my face, all right? Roll a ping pong ball across my face. And when is this ping pong ball travels across my face, past my face, I go like this. What happened to the ping pong ball? I just blow. It moved. It got deflected, right? It got deflected to you, let's say to your face. Now, switch from the ping pong ball to a bowling ball, and you guys know that's heavy, really heavy. So roll the bowling ball past my face, and I go do the same thing. Try to deflect it. What's gonna happen to the bowling? It will slightly, or you might say it doesn't affect it, right? But it slightly move a little, but it's much less than a ping pong. Ping pong ball is light. Once it goes through my face, pass through my face, I go, it got deflected right away because it's light, right? The key word that I'm looking for, trying to explain it to you is inertia. Okay, so the heavier particle have higher inertia than the lighter particle. The lighter particle get deflected easily. Right there, the heavier particle doesn't get deflected easily. All right, so it doesn't deflect. The angle is not as wide as the lighter particle. And Aston came up with they must have the same nucleus. They are the same nucleus, but different mass. Right, and the number of protons cannot change. This is just neon. They gotta have 10 protons. But what changes is the number of neutrons. Okay, so he said, oh, this gonna be an element that have the same number of protons, got the same element, but different number of neutrons. That's why they have different masses. Okay, and he called them isotope. Right, just to help you memorize this a little bit. P right here, the same proton. What's the difference? The neutron is different. Yeah, isotope. Yeah, same proton, but the neutron is different. Okay. All right. Let's go to. We have one more video. I think 1 or 2 more.